Well, hello, welcome to section 4.3 of probability and statistics. So we are in the midst of probability. So section 4.2 was about the addition rules, right? We talked about mutually exclusive things or not mutually. Section 4.3 is multiplication rules and conditional probability. So we've got independent events. Independent events means that an event does not affect the next event happening. So the probability of A does not affect the probability of B. For example, if I roll a die and get a 5, and then I pick up that die again and want to get a 3. Rolling the 5 has no effect on what I get for the next roll, whether it's a 3 or not. So they are independent. They do not depend on each other. We'll talk about later in the section about dependent events. So independent and dependent events. So here's our first multiplication rule, our probability rule for independent events. It goes like this. The probability of A and B is equal to the probability of A times the probability of B. So I don't know if you remember, I hope you do, back in section 4.2, we said that whenever you see an OR, the probability of A or B happening, it's an add, right? Whenever you see an and, it is a multiply. I'm going to ask that a lot, so keep that in mind. An or means to add in section 4.2, and means to multiply. And of course, I got a little fancy with my symbols here. So the probability of A and B, the intersection of A and B, is the probability of A times the probability of B, or if we want to really sum it up, it's the product of the probabilities. This can go on to more than 2 events, 3 or more, so the probability of A and B and C will be the probability of A times the probability of B. So it goes on and on. We'll probably just stick to 2 events. Maybe I'll throw a 3 in there every now and then. So I got really lots of words here. There is something that we have to talk about, and I don't know if it'll make sense to you yet until we get to later on. But so if we select a small sample from a large population, let's say we select 10 people from Marine City out of the whole United States. So it's a small sample, large populations. The subjects are not replaced. So I'm going to pick one person, and then I'm going to pick a second person, and everybody, those 10 people, stay out. The probability of the event occurring changes so slightly because the population is so large that it's considered to remain the same even though it's really not independent events. This not replaced thing is kind of a big deal. So if we say, let's say that 24% of American consumers like a particular brand of toilet paper, then the probability that 2 Americans selected, even without replacement, the probability that they both prefer the stated brand, so the probability of, I'll say, likes and likes, is equal to, now I did this sneaky here, but it's an and, right? The probability that the first person likes whatever it is, that toilet paper, and then the second person likes that toilet paper is going to be, our probability is written as a percentage this time, but we can still do that. The first one is a 0.24. The second one is a 0.24. So even though, because it's such a large population and we're picking a tiny little number out of them, we don't worry about this without replacement, whatever. So keep that in the back of your mind if you've got a really large population. I believe that calculates out to something like a 0.058, so 5.8% of the population of that sample would like, that the probability that they both like that kind of toilet paper is about 6% probability. All right, so let's look a little bit more general example here. So probability with replacement, I probably should have written down with replacement way back at the beginning when I said independent events. So I'm going to pick a marble out of the bag, and then I'm going to put that marble back in before I select my second marble. So with replacement is really important. Always look for that. when you do the problems. So it says, I've got a jar of 5 reds, 3 greens, and 7 blue marbles. 1 marble is selected, its color is marked down, and then it is replaced. A second marble is selected, and its color is noted. Find the probability for each of the following. So if I want to select 2 greens, let's put this in terms of what we're looking for. I'm looking for the probability of a green and then a green, right? So that's what it's saying a lot shorter way, 2 greens. So the probability for that first green, remember it's always favorable over possible. We're still going back to that section 4.1 stuff. So how many favorable or how many greens do we have? 3 out of how many marbles are in this jar? Looks like, what, 15? I put that green marble. I always make the assumption, yes, that did happen. I picked one of those 3 green marbles out of the 15 possible. The second green, so that's that one. The second green then is I put that marble back in. So how many marbles do I still have in my jar? I've got 15 because I stuck that one back in. That's why that's important. And there are still 3 green marbles. This and right here tells us that we are going to multiply those guys. So I get 3 out of 15 times 3 out of 15. I believe that's going to be like, what, 9 over 225 simplifies down to 1/25. In these kinds of problems, I'm going to like to keep them as a fraction. If you want to turn that into a 0.04 or a 4%, you can do that, but sometimes it just gets confusing. Everybody getting the hang of those ones. So we always make that assumption. Remember, it is multiply whenever you see that and we're looking for that with replacement. So again, I know it might not seem important to you now, but 2 cards are drawn from a deck with replacement. So we got to go back to that section 4.1 deck of cards if you need to. I'm going to draw 2 cards. So I'm going to draw one, I'm going to put it back, and then I'm going to draw a second one. What's the probability of drawing a queen and then an ace? So, and notice it has the word and in it. Probability of a green and an ace. And tells us to multiply a green. I was still on the last problem. That's supposed to be a queen. It rhymes, but. So what's the probability of drawing a card, the first card, and it is a queen? Well, I have to look at my deck of cards. I know for possible, there's always 52 decks in a card. And I know if I look at my chart or if I know cards, there are 4 queens, one of each suit. So I put that card back. I make the assumption I got one of those 4 queens out of the 52 cards. And then I go to the ace. So how many aces are there in a deck of cards? There's 4, one of each suit. And there's still 52 cards in that deck. The and tells us we're going to multiply those 2 things together. So hopefully you know your fraction button on your calculator or use parentheses with the divide. And you end up with something like 1 over 169. Again, I keep this as a fraction. If you turn it into a decimal, I think it's like 0.06 or something. Correct me if I'm wrong, but I think it's about 6%. So you have a 6% probability of drawing a queen and then drawing an ace, putting those things back in. All right, let's jump down to number 3, because number 3 is that really wordy problem that we talked about earlier. A study has shown that 39% of people will be diagnosed with cancer in their lifetime. If you choose 3 people at random, it's a super large sample, right? This is all people. If you choose 3 people at random, what's the probability that all 3 will be diagnosed with cancer? All right, so here's my probability. It's at a percentage instead of a decimal or a fraction. But I'm wondering if probability of cancer diagnosis and a cancer diagnosis and the third person has a cancer diagnosis. So even though this is without replacement, my population is so large that if I took one out or whatever, we put it in the with replacement, but if I took one out, it's not going to affect that calculation. So I'm going to end up doing the first one with cancer would be a 0.39 probability. The second one would be a 0.39 probability. The third one would be a 0.39 probability. So if I'm asking about 3 people, I have to have 3 things. Since it's ands, I have to multiply those guys together. And I believe this ends up being a 0.059 maybe. Check me on that one. Also, just to be sneaky, if the study has shown that 39% of people will be diagnosed with cancer, I could ask you what's the probability that someone is not diagnosed with cancer. So if 39% of people are, then that would make what? 61% of people who are not. So they sometimes throw a little sneak attack in there, so watch out for those. All right, so that is the independent or with replacement. Dependent is the first event affects the second. Typically in problems like this, you will see the words without replacement. And we'll talk about that in just 90 seconds. So first of all, let's make sure that you can tell which events are dependent and independent. So having a large shoe size and a high IQ. Do those two things, does one have an effect on the other? Does one depend on the other? As far as I know, there is no data that indicates that there is a correlation, so those would be independent events. A parent being left-handed and having a child being left-handed, I mean, this could be up for debate, but I do believe there's a little bit of a genetic influence. I know it's not always. My sister has four kids, 2 of them are left-handed, and neither her or her husband is left-handed. But I was kind of just trying to find a dependent example, so I'm sorry if I offended on that one. How about C, getting a raise in salary and purchasing a new car? That could potentially, right? That could be a dependent. Maybe you were waiting. New cars are very expensive, so I could see how that would be dependent. And let's go back to the basics here, people. Rolling a die and tossing a coin. Do those two things depend on each other? Getting something when you roll a die and something when you flip a coin, definitely independent. I will try to avoid controversial statements like B from here on out. Just wanted to make you think about it. All right, so conditional probability then. This is our next multiplication rule. Conditional probability is the probability that B occurs after A has happened. So we're making the assumption that A happens. We're talking about without replacement. And so therefore, we have things change for event B. So here's my notation. The probability of B line A, it means the probability of B given that A has happened. And here's our formula. So notice, I've back to my Venn diagrams here. This is my 100%. Everything happens within there. I've got bubble A. I've got bubble B. I've got my overlapping union of A and B. But now here's the thing. The probability of A, or probability of B, if A has definitely happened. So my formula for that is the probability of A and B is the probability of A multiplied by B given that A. I wish I had given you the formula that we're going to do in just a minute first, because that's the formula that kind of makes it all make sense. So the probability of A and B, that overlapping, is the probability of all of bubble A times the probability of B given A. And that's hard to see on a Venn diagram, right? So we need to look at that other formula and see where that comes from. All right, so let's do a quick little example before we get there. So probability without replacement, super important. So we've got ourselves a deck of playing cards. Go back to your sample space if you need to. 3 cards are drawn and not replaced. Find the probability of drawing 3 10s. So I'm saying the probability of a 10 followed by a 10 followed by a 10, right? I'm going to just write it as 10 and 10 and 10, but I have to definitely remember that things are not replaced. So, drawing 3 10s. So what's the probability of this first 10? This is the easy part. Well, how many 10s are in a deck of cards? Because remember, it's favorable over possible. So there's 4 10s, right, out of 52. Here's the thing. I'm not going to replace that 10. Oh, I wrote 10. It should be 4 out of 52. Sorry. I'm going to not replace that. I make the assumption that the first 10 happened. So now how many 10s do I have left for my second draw? I've taken that first one out, so now I've got 3 10s. How many cards do I have in my deck? Because I did take that card out, right? So now I've got 51 cards in my deck. So now I'm going to my third 10, and I'm saying, all right, well, I drew the first one, I took it out. I drew the second 10, I took it out. So now what do I have left? I have 2 10s left. Out of how many possible cards am I drawing from? That would be 50 cards. So now it's an and, so I've got multiply in between each one of those. So now we're going to grab our calculators. We're going to figure out, I believe that's a 1 over 5525. Hear the click of the calculator buttons. If you turn that into a decimal, I think this is the one that comes out to like 1.8 times 10 to the negative 4. I don't love that as an answer. I don't love scientific notation as an answer. Do you understand how scientific notation works? This negative 4 tells you how many decimal places we're moving left because it's negative. So 1, 2, 3, 4. I'm going to put zeros in place of that. So I could say that that's about 0.00018 or 0.0002. I'll make it a 1/8. Again, that's a teeny tiny probability, right? So we don't have much of a shot of drawing 3 cards out of a deck and all 3 of them will be 10. Just really not going to happen, or highly unlikely. Is it impossible? No, because if it was impossible, our probability would be 0. But look at how close to 0 we are. So it's highly unlikely. So why does with or without replacement matter? What does this affect in the problem? It definitely affects the possible outcomes, right? With replacement, you have the same number of possible outcomes. So this affects possible outcomes, affects your sample space. And in the case of example A, it also affected our favorable outcomes. We had 1 less 10 in the deck of cards after that first draw. So we had to watch out for that. So you have to watch those. Look for with or without replacement, because without replacement affects the possible and favorable outcomes. Not always favorable, but always possible. So we can talk about that. All right, so conditional probability. I wish I had done this formula first. I've got the same Venn diagram over here. Here's the formula. Here's how you figure out the probability of B given that A has happened. So A first and then B. And what's the 2 of them? So it's the probability of A and B. So my overlap, this part, divided by my whole probability of A. That's going to give me the probability of B given that A has already happened. Now when I do these problems, I have to really think about what is B, what is A, what goes where. So if we do a quick example, in a recent year, 99% or 0.99 of the incarcerated population is adults and 0.07 of the incarcerated population is female. If an incarcerated person, you know, incarcerated, right, in prison person is selected at random, find the probability that the person is a female given that the person is an adult. So, probability of B given A, in this particular case, find the probability that the person is a female given that it is an adult, so not a juvenile. I'll put AD. Not a juvenile offender. So if we're going to do that, then we're going to do the formula, the probability of A and B. So the probability of adult and female divided by the probability of adult. So let's see what we've got to fill in. What's the probability of adult and female? 0.07. I don't know why I put parentheses around that. 0.07 over the probability that it's an adult, which would be a 0.99. So do myself a little dividing. 0.07 divided by 0.99 is like a 0.707. So 71% probability that the selected person is a female, given that we have drawn an adult. So we're only looking in the adult population and then female. So those ones watch out for. There's some interesting ones. All right, last but not least, let's talk about these at least problems. These ones are interesting and they go along with that complement. I think that was in the last section we talked about that. So we're going to use multiplication rules for at least. It's basically a big problem. And the probability of at least 1 is equal to 1 minus the probability of none. This is a complement thing. Let's say I've got a bouquet of, what does this give us? How many flowers are there in this example down here? We've got ourselves 6 roses, 9 lilies, 7 daisies, and 6 orchids. What is that, 28 flowers? So let's say I've got 0 to 28 flowers. I want to know the probability of at least 1. So at least 1 is 1 or more, right? So I want to know the probability that there is 1 or more flowers that I'm choosing. Well, that seems like a lot of work because I'd have to do the probability of 1 and 2 and 3 and 4 and 5 all the way up to 28. However, if I just found the probability of this little piece of 0 flowers, all of our probabilities add up to 1, so I could do 1 minus that little piece and save myself some work. So let's look at letter A. It says, let's see, if 4 flowers are selected at random and not replaced, that's important, right? That's going to affect our possible and favorable. Find the probability that at least one of the flowers is a rose. So if we do this, we'd have to do at least 1, so probability of at least 1 rose. So I could find the probability of 1, 2, 3, 4, 5, or 6. However, I think I might save myself some work if I do 1 minus the probability of no roses. That's not just a one-step problem, though. We're just going to do this one if you need more space. So the probability of no roses means, or 1 minus the probability of no roses, means that we've got the probability of 1 minus, let me do it this way so I don't lose you. The probability of no roses, so when I choose 4, I need to do the probability of not a rose, and not a rose, and not a rose, and not a rose, right? I'm choosing 4 flowers and I'm not replacing them. So unfortunately, it's just still not one problem, but it's better than what I had before. So the probability of the first one being not a rose, there's 6 roses, there's 28 flowers, favorable over possible. So the first one would be, let me put that around there like I did. Not a rose would be what, 22 flowers out of 28? That's my first one. The second one, did you notice in the directions it says we're going to select a flower and then we're not going to replace it. So what does that do for the number of flowers that we've got in our bin or whatever it is, our bouquet? we've now got 27 flowers. How many of them are not roses? 21. So that's that second one. Third pick, not a rose. How many roses do I have left? Or how many, sorry, not roses do I have left? 20 out of 26. And my last pick then, I've got 19 roses or flowers that are not roses out of 25. So I need to do myself a big old multiplication problem of all of those. I think when you do your whole 22 over 28 times 21 over 27, blah, 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 I believe that comes out to a 0.3573. I could have left it as a fraction. The denominator gets a little ridiculous. So the probability of at least one rose is going to be equal to 1 minus that probability of no roses. So I believe that's going to end up to, if my math is right, a 0.6427. Check my math. But I think that's what I've got. If that feels overwhelming, don't get stressed. Let's talk about, we'll do more practice with those and we'll talk about those more. But it is kind of a cool concept and we will use it some more. If we can make our math a little bit easier, let's make our math a little bit easier. So, all right. Notice letter B, it says the probability that all four are roses. So we do the probability of a rose and a rose and a rose and a rose. Question 3 asks us, which one is more likely to occur? So we could compare those probabilities at the end. You might have a guess which one's more likely to occur, but that is the end of 4.3. Look for replacement or not replacement, and tells you to multiply. Those are the two biggies, and then you just have to run through and figure out favorable over possible. That's it for section 4.3. Thanks for hanging in there. Let me know if you've got any questions.